How you doing, guys? This is Andrew at Flory PB, and I think in the first video we did this year, I was showing you guys some of the parts we were trying to start making, and I promised that I would do a video of an actual design and concept of how I want to get to a part, and I want to try to start this video right now. I'm not sure if I'm going to finish this video. Might post up in two parts, because it's this is more design, and I'm not going to go into some crazy design, like make sure it's perfect and all that kind of stuff. I'm going to do a relative design, because ideally I'm fighting with something that it's already predetermined the space I'm in, so I have no real control over that. I'm going to try to make a part that's relatively as good or better than what's there, and it's going to be a relative term part. I have ways to test it later, which we'll get into, but an externally adjustable LPR is something that people always complain about with Angels, and wrongly complain, because you don't need to touch your fucking LPR pressure after it's set correctly. You don't need to do what you do with an autococker and continuously adjust it and try to make it work. It's set to the pressure range it needs to be. It's going to go. Stop worrying about it. And, you know, Angel LPRs, if you've seen previous videos of mine, they're great. They're probably one of the best LPRs ever made, if not the best LPR ever made. Their mini regs, total fucking garbage. But the LPRs they made were incredible. If they made the mini reg the size of the LPR, it would actually probably be a decent regulator. It wouldn't have the problems that it does. And I always feel like they compensated for that in their initial design by making such a good LPR. And back in the day, you used to be able to get a free flow error mod, which all it did was it took this. They don't have one for this. You can get a couple external LPRs for this now, I think. The JDS or AKA stuff. I think you can still get LPRs for Angels. Actually, I think I have one that I want to test against what I'm doing here. But my goal here is to make sure that the LPR stays in the same bore, because that's what matters. That big bore that the Angel LPR is the reason why I always say that it's one of the best LPRs, you know, in the sport. It's such a massive bore, and I think I explained this once before, but that was a long time ago. You have a few things here. When the air comes in, it makes pressure. What pressure is, it's PSI, obviously. Hope you guys can see this. Let's zoom in. Pressure's in PSI, which equals pounds per inch squared. Pressure is also called something called stress. So PSI is pounds per inch squared. In standard units, I don't know about metric, it's pascals, or so, yeah, pascals, but I don't really like dealing with metric if I don't have to. Civil engineer here. But pressure is stress, and what stress is, let me write a little bigger, equals force, which we're going to use F here, divided by an area. So pounds is force in standard USA base units. You have a force, and that's a pound force, and your area is an inch squared. So the inch squared area, this is where everything goes, because area of a circle is pi times d squared over 4. So the bigger your diameter is, it exponentially grows your area. Basically, it's almost a 4-time factor. You double your diameter and you quadruple your area, basically. So that's super useful when it comes to pressure and to how these things react, because if you go back to Newton's laws, force equals mass times acceleration. And that's a different A. This is this is acceleration. So ideally, your force is going to be set by the pressure, because PSI is what's going in. If you have 100 PSI over a known area, it's going to generate stress times area is going to equal force. You're going to know this force to put into this side of the equation. The M is mass, so how much does this weigh? You have to do a weird unit conversion to get gravity involved. But for simplistic reasons, we're not even going to care about that. So force over M equals acceleration. M's going to be a constant, because you can't change the weight on it that easy. You can change the force on it a lot easier. So the more force, the more acceleration. The more acceleration, the faster the reg reacts. Now, if you want to really get involved, there's going to be some oscillation from the spring and stuff like that, but that's a much larger, I guess, Taylor series would be the best way to think about that. But we're not going to bother with that. That's not what we need. We have something that works great. We want to not affect the area. If anything, we want to, we can't increase the area, but we can reduce the mass. And we want to make it in a way where it's adjustable externally without being like a free flow error mod where you had a Cocker LPR sitting on the front of it and a fucking tube going into it. Something clean, something that looks stock, something that should be the way it was. And that's the goal here. So basically, there's a few ways to make an LP or any kind of regulator. This is an inline regulator, just like most standard high pressure regulators are. And that's super effective. Most LPRs, though, operate on a Schrader system. So you're going to have it's called the open bore of the Angel. We're going to put a piston in the front. Make an O-ring groove. The bleed hole is going to be about here. I'm just roughing this in to bleed out. We'll have a shaft coming through, which has some kind of end which fits in here, which would be interacting between these two here. This can all be open space back here. And then this needs some kind of body that's smaller than this end. So when the pressure comes past here, goes in here, pushes forward, this is going to have the spring in front of it instead of behind it. So you can adjust the LPR from up here by putting more tension on the spring or less tension on the spring. When the pressure comes back here, it's going to push this way, and eventually it closes itself, which is a similar way a Schrader valve works. But I think we can make this work. We can make something a little bigger and lighter so it works the way we need it to work for an Angel. So that's the general scheme. I want to design it, and I want to see if I can make something fit. And then we're going to end up machining it and trying it out, and then hopefully running some tests on it to see if we fucked this up or if it's doing better. But imitation's the highest form of flattery here. We have to figure out our dimensions that we have in order to know what we can do. And I have the parts here, and I'm going to use an A4 style Angel just because the LPR is on this side to start, and just easier than trying to interact with the valve to start. Just make everything less. But my ideal part would be to make this for older Angels. So let's and of course we try to make this for basically every kind of Angel, because there's no reason not to. Let's get my depth to the face of the piston, or sorry, not the piston, the LPR housing. 8965. So our cavity is from the threads front to there is 0.896 inches. You're dealing with something like this, metric or English doesn't really matter in when you're in thousandths of an inch. It really doesn't matter. It's a fucking number you're gonna read. So I don't get why so many people are so into just using the metric system for shit. Because your bore's roughly 0.715. I care more about this bore and how this fits. 0.702. Plus the O-ring on it gets to that 0.715. The ID kind of matters, and you can get in there with one of these. Not the most accurate tool, but accurate enough for what we're doing here. A couple thou is well within tolerance of what you need. So 0.593, then you have your O-ring that's going to seal against your bore. And we could check that kind of tolerance there. But your piston face, we'll call it 0.705, make it a little bigger. It's got the room. And your O-ring gland. .593, I think I said. And we could check multiples of these to see what our tolerance stacking, or see what our tolerance is throughout the range. Let's call it 0.59. So that's that piece. I need to see where my threads end roughly, so because I can't put it in the threads, I need something that goes to the threads, but it doesn't have to seal anymore because the face of this is going to be, naturally you want it to bleed, and if this starts leaking, it'll start leaking there, which allows it to bleed. But this is going to help us figure out our throw that we're going to have. 0.2. So let's 0.2, call it 2, just to have a little extra space. If we can't do that, we can't do that. So 0.22, 0.896. We need to put a body in, this is in front of the body, so this is going to be the space that we have a volume chamber that's going to be for the air. So we have a decent volume chamber too, because that's 0.676 inches. So there, that's that. That's the rest of it. So we got to put a piston head in there that can go from basically closed in here and then push up that way. And the piston head has to be, at the very least, 0.172. Let's call your min, we're going to call 0.175 inches. And we're going to try and make all this out of aluminum, or maybe out of 70-75 aluminum if it's a little too weak. And we'll just run it that way, and it's going to make this significantly lighter, which is going to increase our speed, our acceleration, because the mass goes down, but the force stays the same. But it increases it linearly, where if you increase the area, you increase it exponentially. So you get a lot bigger gain out of your area. But again, this is probably one of the biggest piston areas in paintball. I think ever. This is one of the biggest LPR pistons that there is. Not HPR, but LPR. This is huge. Maybe they have some bigger ones, but it's really big, and it's really a solid LPR. So I don't want to ruin that. I want to improve it, if anything. But we have that. And now this body is going to need a second O-ring on it, probably. But it's 0.485. LPR body. .485 inches. And I'm pretty sure you can fit 2 O-rings on here because it's 0.14. Yeah, 0.16. So you can fit a second O-ring on the front of this, so you're not bleeding air. So we need an O-ring groove in the front and O-ring groove in the back. Or else you're going to bleed air out your pin. Pin isn't located in the middle, which kind of sucks. but there's nothing telling me I can't go forward more to locate this thing better. So the rear, there's going to be the pin somewhere in this body. We will determine that as we go. This body, 0.702. We'll make it 0.705 as well. O-ring 0.59 inches as well. 2 O-rings. That's the outside of it. I have to size the pin a little better. We'll probably pre-size it in a body, slip the thing in, and make sure it seals and put a pin in it kind of deal. We'll pre-size it in a body before we get an overall dimension on that. Just because it's such a hard thing, because it's an offset pinhole, it's definitely harder to do. Once we figure that out, it's more of a machining issue than just a straight design. It doesn't really matter to us here that much, but it does interfere with some stuff. Like roughly it's 0.213. So the pin's gonna go in 0.22 inches just to have a little clearance and to be safe. Ah, fuck it, 0.25 inches. Which means that this is 0.705 minus 0.5 for both sides of this thing, because you can't have the airflow somewhere weird like that to flow through the center of it. So you're going to talk about you have a hole of 0.205 inches to be safe, which is bigger than that, which is good. And this hole in the middle here is rather tiny, 0.082. Ridge hole. That's the air transfer hole, so it's 0.082. So the area of that is 0.082 times pi over 4. Let me grab my phone. 0.082 squared, sorry. 0.005 inches, so that's not very big at all. And I have this to be more accurate, but we don't really need the accuracy here. It's not. Let's just confirm to see if this thing's fucking up too much. $702.55, perfect. Within a thousandth of each other, that's more than good enough for me for this kind of project. On a piston body, I know the hole in it is going to be .2 inch hole through this thing. That's going to let the air rush in. Now I need this piston head, which is going to be on this side, to be attached to a piece that gets threaded into it on this side that can close when this builds up the pressure that it needs. So that shaft needs to be 0.485. Plus I have plenty of room back here to do this. This is going to be a spring decision we got to make later, is figure out the spring rate we need and the stiffness of that spring to make this work based on the force that we're pushing it and how far we want this thing to go before we close. That's going to affect the adjustability of it, but hopefully we can make an LPR for this market that can adjust between 30 psi to like 100 psi. And I would like to make it so it doesn't really adjust much more than like 100 psi. That would be like ideal. But that's more of a, that's not this starting game. The starting game is going to be size up the body, size this up, and then we'll do a second video probably on figuring out the spring rate that we want and the size that we want of it. We can do some pregame on that too. But 0.485 plus we have a cavity of 0.676 to the threads, but that's not to the through hole. Let's try to go to the through hole because we have to be on the other side of the through hole. So let me try to get this in the light for me. Let me pull this off. I can stick something up through the through hole to hit. Oh. Okay, this is going to be trial one. Figuring this out is only going to get us in the ballpark. They're going to do some testing and see if we made something that's it's actually worth our time without trying to go into a deeper analysis of it. Just solely basing it on we're keeping our same area for our piston, and well, relatively the same area for our piston. Might actually get a little more technically, which is good. So we have a little more area, which is great. And then we'll have a little more, we'll have adjustability, which is fantastic, which is what we're going for here. We're trying to get a little more area of it and make it a little bit lighter. It's not perfect, but gives me a hard stop. 0.48, 0.4. So let's make sure we're back from that a little bit, and it's 0.48, but that's to this, which isn't ideal. We're gonna rough it in, see if it works. If it looks good, we can tweak it from there. But we'll call it 0.43. That's going to be, our gap is from 0.22 to 0.43. So then our actual running gap is going to be kind of stuck. And we can cheat this to push the back of this into that hole a little bit. So we can make this work. But our running gap is going to be 0.21 inches to house this whole thing in. This thing itself is 0.17 inches, 175. So the gap we're going to have to close has to be 0.21 minus 0.175. Getting 210, 175 is 0.025. Fuck it. .035 inches, which is like a 32nd of an inch. So we have this to play with, which is gonna be kind of hard to try to get the pressure range we need out of that. So we might have to make this pressure range lower, and we'll see if we can even do this. Again, we're just kind of going off the cuff to see if we can actually figure something out here. Ideally, we can go a little further this way, and we can cheat it back a little further that way to make this work. So there is room to play. This is just initial idea and thought. Probably bring it to like 0.04 just to see if we can do it. I'd be more comfortable with like 0.06, but I really can't get there. Like a 1/16 of an inch, like 0.0625. But I don't think we can really get there. We're going to try it and see what happens. If it's a failure, it's a failure. But we're 0.43 to the face here, which is going to be the start. The backside here, this is side 1, side 1. That is going to be a gap of 0.896 minus 0.43, 0.466 inches. Back here, so that's the gap to the face here. Then that's going to be an additional 0.466 plus 0.485. 0.951 is, this is the shaft. Should put some kind of closing end on it. Something sharp. We might make this out of Delrin in order to give that a shot and make it out of Delrin, and then maybe we can make this seal up against, which would be pretty cool. So 0.0951. This shaft needs to be under 0.2 inches in diameter. So like this would be 0.1875, which is a good size. It allows me to get like a 10/32 thread into here. Which would be good. The front of that will have to be basically almost all the way through it. Fuck it, all the way through it. 0.175 thread. Plus to the center here is going to be a total closing. We have 0.035. We call it 0.04. We'll make that 0.035. So it's 0.951 plus 0.175 plus 0.035 inches there. 0.175, because we'll just seal that with some Loctite for the initial one. Maybe we'll do something a little smarter later. So the whole thing has to be 1.161 inches from there to there. And that's a relatively tight dimension that we're going to try to run on that. We have 0.035 inches of travel until we hit that. And again, we were saying that we can probably sneak about 0.4 inches out of this setup here. May have to take a little bit off here. We're going to play with it until it actually works. And that's the prototyping stage, basically. So the first thread, and that's pretty good. 0.175 times 32 is almost 6 threads in there, which is over 3, and that's basically all you need. So you almost doubled down on that, which is good. So if you have 6 threads, this head would be made exactly to the dimensions of this head here for the piston head. The piston shaft will be 0.1875, and my area is 0.02. On 0.2, so my whole hole is going to be 0.2 times 0.2 times 3.14 divided by 4, 0.0314 minus the area of my piston, which is 0.1875. Oh, motherfucker. Times 0.1875 times 3.14 divided by 4 is 0.0276. 314 minus 0.0276 equals my area of hole is 0.0038, which kind of sucks. So we'll reduce this a little bit to be basically 0.175 then. We'll try that again. Divided by 4. It's 0.02. Sorry guys, I don't know where I lost you on here. Let me just recap. we're sizing the shaft of the piston, and I was going to go with 0.1875, which is 3/16 of an inch, because it's just easy. My through hole is 0.2 that I'm running, just to keep it conservative and undersized a little bit. I tried to get my area to match or beat the initial area, that's the through hole on these. It was a little undersized by 1,000 inches squared. So I dropped this to 0.175 inches, which still works with a 10/32 thread for the most part. Might have to cup it down a tiny bit. And I made my area work around 0.007. So I might be able to get this up to like 0.18 just to make it a little bigger, a little stronger. Because next we have to consider the load going through there. If the marker is at 80 psi, say, at 100 psi, because we don't want this to fail, right? 100 psi acting on this, so times that by 1.5 equals 150 psi. My whole shaft area is 7.2 inches, just to be a little conservative. Squared times pi over 4. 0.407 inches times 150. Call it 65 pounds acting on this setup as it's pushing this way. It'll be pushing with about 65 pounds of force at best, and it's going to be less than that. That's probably going to start blowing the solenoid, so we don't want to get that high. But we got to ideally make sure that we're not going to stress out that tiny piece there. So that shaft is 0.175 inches, which is the area of that. .02404 inches squared. The stress that makes is 65 pounds over 0.02404. 0.02404 equals 2,704 psi, which is nothing because aluminum is going to get you about 30,000 psi or 30 ksi when you're yielding. So this is well underneath of the load limit of that, so that's not a problem at all. We can definitely go that thin or thinner if we find that more air flowing in to start is actually an improvement on it. We can go even thinner on that, which is cool. I don't like the way that thing works, but so that's ideal. That's the smallest part that we're gonna have a problem with would be that. That's okay. So that's the thinnest part. That's the part that's gonna yield or break, and that's the weakest part. So that's perfect. Fuck it. Let's assume that we get let's say it doesn't seal, and you get full tank, 825 psi. Fuck it. You have a CO2 tank on it. It's been in the heat all day. 1400 psi. Real fucking scary, right? So 1400 psi. That's 0.407 is my area. What the fuck did I do here? Yeah, 0.407. 0.407 times 1400 is 570 pounds. 570 pounds divided by 0.02402 is 23,710 psi or 23 ksi. So that's still under the yield strength of the aluminum that we're going to use for this part. So even if everything blows, no regulator, that LPR is not going to shoot forward into the threads, which are then going to catch it, and it's not going to actually break the LPR. Fine, overkill, but just the size that works. We can't go any thinner realistically. It's really fucking thin the way it is. So basically we'll have to make at the end of here some kind of tapered piece that we'll call it a 45 degree. 30 degree. We'll call it a 30 degree taper because I can get a 30 degree ream. we'll make this a 45-degree taper. Because if you have the 45, which is going to be here, let's make that more 30. Ideally, if something looks like that, if this thing is a 45, so it's steeper, when this gets forced that way, it's going to close and it will pinch in two spots, and it's two cones, so it should pinch pretty concentrically and be nice with how that works. And that will keep this straight with one O-ring on the front, will help keep it straight. Now we could probably add a second pivot point, because we can make a little, we got to make something that comes off of here a little bit. And we got to try to make sure that, let me think about it. If we tighten it, it raises the pressure, which is good. Because we wouldn't want to try to tighten this, and we wouldn't want to make this loose and it raise the pressure, because it might back the threads out. So if it tightens, it raises the pressure, which would be pretty good. Now the concern is I have 0.035 inches of travel. And I have, realistically, I need to make 80 PSI. On this marker. I can size the spring differently for different markers, but I need to make 80 on this platform. Let's go 90. Let's say I need to make 90 PSI. So at 0.35 inches, I need to make 90. I need to get 90 PSI out of that, which seems doable. I need to find a spring rate, basically. That's going to be the next video. I have this much travel. This is my end PSI. In that travel, I need to have something that is going to compress off of the force that's going to generate. 90 PSI will generate times 0.407 times 90, 37 pounds of force in 0.035 inches of travel. So it's a pounds per inch thing you want here. And that's going to be my spring rate. I need to find my spring rate of pounds per inch to make this true, this relationship here. Which isn't too bad. Let's see. 1.035 divided by 1. I'm an idiot. 0.035. So I need to divide that. 37 divided by 0.035. It would be 1,057 pounds in 1 inch. Because it's 37. I think that's how spring rate's going. Maybe I'm fucked up on that. Again, let me do a little research on that to figure out what I want to do. But I think this is the kind of spring rate I'm looking to get. Which isn't much different than probably what these beveled washers are giving me. It is something probably close to that. And that might be what way we have to go with it. So we'd have to size the screw and size everything so we can get enough force to torque that thing to get this kind of load. And actually, 0.35 should be my lowest, now that I'm thinking about it. This is, again, off the cuff. I apologize that I'm a little all over the place here. I'm just trying to show you what goes into the general idea and design here. 0.35 should be my full travel. Yes, that's the max load it can give, so I have to tighten it up for that. And the minimum, we should have 40 PSI. I gotta rate the spring, because I can compress the spring more to get this, or I can loosen the spring more. The spring could be longer to get this fluctuation range that I need in the front, just based on how I torque the spring down. So it's 40 PSI says you're low for this, which seems reasonable. 0.4 times 40. So that's like 17 pounds. I call it 16 pounds to be a little under. So that's a spring rate of 400, 7.2. So this is me with my spring not very taut is going to be that, and then me with my spring taut is going to be something like that. So we need to size the spring to fit basically in a little volumizer. Find an appropriate thread for the outside of that volumizer. Probably a 5/16 or something like that. Something not that big, but big enough to actually get a good grunt on it if you need to without... inclined plane like a screw can give you a much large amount of load, and you don't realize how much load it gives you. So like something like a 5/16 is probably going to give you enough load to be able to achieve something like this without being too radically hard to turn. But again, that's stuff we got to look at the next one. Just want to throw the initial idea out here in the initial design phase. And let's real quick just draw the initial sketch up of what we're looking to do here. Real rough stuff here, real rough. Looking at the piston head out here. You have the shaft going through. Something like that. So this doesn't move. This does. You have a nice spring of some kind in front of it. I don't know if this, of course, is in the body or in the volumizer and body kind of area that we're going to make. And then at the end of that, we'll have a nice beefy threaded section here with a set screw and some kind of plate on the edge of the set screw to put pressure on the spring to make this harder to close, which increases the LPR pressure. The body vent hole to the LPR will be in here, so we'll have a decent volume in there. And the trick and the goal is to size this spring with the room I have. And that's going to be the next thing I look up, is I'm going to try to get some spring rates and some spring sizes and figure out if this is feasible to do something like this, or if we have to start rethinking this and going in a different direction with the piston. I'd really like to keep the piston the same size in the body. If I have to, we can reduce the piston size, which sucks. I don't want to do it in order to fit it in a volumizer. But then it's no better than the other options on the market, so I don't want to do that. Unless we make the volumizer fat, which is a possibility too, and then the piston head has to go there and the volumizer has to be two pieces. There's other ways around this problem, but I want to try to make this as tight and factory looking as we can. And my explanation of that is we'll make a volumizer as two pieces that would keep it the same size as the body, so we can keep this piston diameter. And this just gets longer and it's outside the body. That might be the way this has to go. Make it more difficult to service, which I wouldn't like. But let's try to get it done this way, see if I can figure it out. If not, we'll go that route and start looking at that. That wraps up just this first quick video of... Tell me if you guys think this is interesting. If this is cool in a way. This is not beautiful engineering. It's definitely not like I'm doing Taylor series or doing any kind of Diffie Q of any kind, or doing I'm not doing too much in the way of engineering. I did some stresses, and I'm doing relative engineering based on what exists, the spacing I have for what exists in there, and how can I make something different work in that space. And again, I'm not thinking about oscillation yet or anything like that. If we run into problems, if we build this and it can be built and it works, and we run into problems where I'm not getting the performance that matches this thing, because again, this is a very good performing regulator. But if we can't match this performance, or if we can't exceed this performance in the same form factor, a very close form factor, then we have to start looking into, go deeper into this and see if we can tweak this design, if it's even possible to tweak this design in the space that we have to improve it to where this thing needs to be. But I kind of like where this is going. This will all be hard parts. It will be hard Delrin and aluminum. So you don't really need to service it, hopefully. Hopefully there's enough force to close it. If not, we can switch to a softer plastic or make some kind of O-ring gland if need be. And hopefully we just make an O-ring gland and some hard parts that never actually really die or take so long to die. That's not going to matter, especially with an older marker like this. And make it out of easy parts, because one thing I don't like is replacing the seats here is becoming an issue sometimes. I see on some of the older markers. It's the seats are going bad, and the LPR is creeping a bunch, and you really can't even get the old caps off because they peened over the thread, so you can't get the old cap off without ruining it. So you gotta try to get down in there with a tweezer of some kind to get the seat out, and then you have to make a new seat because they don't just sell seats. So that's kind of an issue. It's kind of a part that, it's not a super wear part, and again, it's a great LPR, but it's something to be wary of going in the future. I'm also going to need a back plug on this. So this thing's going to have to be longer and hollowed out. That might be tricky. We'll have to do something back here like this is done with this back plug, because I need a back plug. And this might be a separate piece altogether that we throw in there first that never really has to leave because it's just blocking the battery. But I didn't think about that till right now. That'd be super easy just to make a separate piece that just slips in there, and then you basically forget about it. It's just a seal that one day, it's not even a dynamic seal, so it theoretically should never die until this stuff dies in like 15, 20 years when the O-ring just gets too soft and won't seal it. But I think at that time it's pretty acceptable to push the 15-year-old battery out and replace that seal. So I might need a secondary, another part that just sits back there and just seals off the battery tube of the marker. But yeah, sorry, I can keep ranting on this. I think this is far enough for the first video. I think it's almost a half hour, if not more. Let me know what you guys think about this. I can do more of this, or I can just shut the fuck up and show you parts after I make them. But maybe someone's interested in seeing the thought process behind it. And just let me know what you guys think. Guys, Andrew at Flory PB, and it's good for now.